Good evening, everyone, and welcome to this problem solving session for the NPTEL course Geology and Soil Mechanics. So, as you know, that this course has been instructed by Professor Priyanka Ghosh from the Department of Civil Engineering at IIT Kanpur, and myself, Shivshankar Nondi. So, I am one of the TAs of this course, and I will be conducting this type of problem solving session on a weekly basis, that is on each Sunday from 5 p.m. to 7 p.m. And I am currently a research scholar in the same department, that is Department of Civil Engineering at IIT Kanpur. So, with this brief introduction, I would like to uh, share this information with you that the structure of this type of session will be like that first we'll briefly discuss about the key topics or the important points which we'll be learning over a particular week. So for example, right now we are at the end of week 1. So first we'll be discussing about, or rather we can say we'll recapitulate the major key features or points which we have learned from week 1. Okay, so then we'll be slowly moving further for the problem solving part. So through this problem solving part will be basically solve a typical or few selective numerical problems related to those topics that will basically help us in better comprehending the course. Okay, so without further delay, we'll start today's session with a quick recap of week 1, as I just said earlier. So may I request you that can you please explain that what are the key topics which we have learned from this specific week, that is week 1? Anyone? Okay, so there are two options right now. So you can either type in the chat box or you can unmute yourself and you can speak freely. Okay. Okay, no problem. If you have gone through the lecture materials or the lecture videos which are uploaded in the course portal, so then you can see. So these are the topics which we have learned from this particular week, that is week 1. So description of soil. So as a whole, we can summarize in this way: that description of soil, engineering geology of soils and their formation, and index properties of soils. Okay. So firstly, under this heading, description of soil and engineering geology of soils and their formation, so we have learned that what is rock cycle and how soil is formed, and what are the different types of soil, like residual and transported soils, then different regional soil deposits of India, and lastly the index properties of soil. So under this index properties, we have learned the basic three-phase soil relationship, then some basic definitions like water content, void ratio, porosity, degree of saturation, and so on. So this particular aspect, means index properties of soils, is very essential, or is that it is the fundamental basis of rest of this course. Okay, so please be very careful about this aspect. And then grain size distribution by sieve analysis or hydrometer analysis, okay, whatever the uh, applicability of the method. Okay, and then consistency of clay, means different Atterberg limits, and then relative density. So as a whole, we can summarize in this way. So these are the key topics which we have learned from week 1. So with this, we'll start solving a few numerical problems. Okay, so the first problem, this is basically taken from GATE examination 2016, and it's mentioned like that: the porosity and degree of saturation of a soil sample are 0.7 and 40% respectively. Now, in a 100 meter cube volume of the soil, the volume of air is okay. So, before moving further, I'd like to inform two things. That is, first of all, I would request your active participation throughout this program. And secondly, if you face any difficulties or if you have any doubts, okay, in between, you can stop me anytime and you can basically discuss with this particular problems, or you can clarify, okay? So coming back to this problem, so this is the problem. So first we'll summarize what are the data given to this problem. So for this problem, the given data are, what are the given data? So the first one is porosity. Okay, so this is a notation N which indicates porosity, and this is 0.7. And secondly, degree of saturation, which is denoted by S. So this is given as 40%, that means 0.4. And the total volume of the soil is also given to this problem, and that is 100 meter cube. Now what is asked in this question? The volume of air. Okay, so that means VA. So VA needs to be determined. Now how we can determine this VA? So as you know that, okay, so we'll basically yes. Okay, so we'll start basically from the very beginning. That is the fundamental definition of porosity and the degree of saturation. Now what is the definition of porosity? Can you please let me know what is the definition of porosity? Okay, so porosity, this is the ratio of volume of voids to total volume of the soil. So this is the definition of porosity. Now here the total volume is given. Okay, so we can calculate the volume of voids. So volume of voids can be calculated in this fashion, that is N times V, and N is your 0.7, that is the porosity, and total volume is 100, so that means 70 meter cube. Okay, now we'll utilize the second information, that is degree of saturation. What is the definition of degree of saturation? So it is the ratio of volume of water to the volume of voids. So that means VW we can calculate by S times VB. Yeah, very good. So S is your 0.4 and VB just now we have calculated, that is 70. So that means 28 meter cube. Okay, so we have calculated the volume of voids and we have calculated the volume of water. Again, we know that volume of void, this is basically summation of volume of water plus volume of air. No? So from the three-phase relationship, the total volume is basically VB plus VS. That means volume of voids plus volume of solids, and in the voids you can have air and water. Okay, so volume of voids, it's basically contributed by volume of water and volume of air both. So volume of air we can calculate from this equation, that is VB minus VW. Yeah, 42, very good. So VB it is your 70 and VW 28. So that means 42 meter cube. So this is the answer. It's a very simple and straightforward question. So the data which are given to this problem are the porosity and the degree of saturation of the soil sample and the total volume of the soil sample. You need to figure out the volume of air. Okay, and it should be expressed in meter cube, which we have done. Okay, so if you don't have any problem, then we can take the next problem, that is problem 2. So the problem 2, uh, in this problem, so the ratio of saturated unit weight to dry unit weight of a soil is 1.5. If the specific gravity of soil solids is 2.65, the void ratio of the soil is. So that means the ratio of saturated unit weight to dry unit weight of a soil is given to this problem, and it's 1.5. Additionally, the specific gravity of the soil solids is also given to this problem, and that is nothing but 2.65. Now what we have to determine? We have to determine the void ratio of the soil. Okay, so we'll first summarize the given data. So the given data here, the ratio of saturated unit weight to dry unit weight. So we can use gamma sat to represent saturated unit weight and gamma dry to represent dry unit weight. So this ratio is 1.5, and in addition to this ratio, the specific gravity, that is GS, is also given to this problem as 2.65. Now by utilizing these two data, we have to calculate the void ratio of the soil. So how we can determine the void ratio of the soil? How we can determine the void ratio of the soil by utilizing these two data? Any idea? Okay, so for that we need to know the fundamental expression of the bulk unit weight. Okay, so gamma bulk we can calculate from this expression, that is GS plus AC divided by 1 plus C gamma W. Okay, before that, can you please tell me what is meant by this saturated, dry, bulk? So can you please tell me what is unit weight? What is definition of unit weight? So it is weight in unit volume, na? So, huh. So unit weight, this is weight by volume. So that means the weight which is basically associated with unit volume of the material. Now we are distinguishing this unit weight by bulk unit weight, saturated unit weight, and dry unit weight. Now what are what are the differences between these three terms: bulk, saturated, dry? What is the meaning of this suffix bulk, saturated, dry? So this represents the condition or state of the soil. So when the soil is fully saturated, then the unit weight of the soil will be bulk. This is the in situ soil. Very good. And saturated, so this is when the soil is fully saturated. So in that condition, the unit weight of the soil will be nothing but the saturated unit weight of the soil. And for perfectly or completely dry condition, the unit weight of the soil will be, yes, very good. So you know all these things, so you are already familiar with these terms. So this is the basic expression by which we can derive or determine the bulk unit weight. Now in this expression, three terms are there: the specific gravity of soil solids, degree of saturation, void ratio. Okay, one more term is there, that is nothing but the unit weight of water. Now, depending on this S value, so this is the controlling parameter here. So this is the controlling parameter. Okay, this S. So as you know, that degree of saturation, what is the permissible range of degree of saturation for a soil? What is the range of soil? Yeah, 0 to 100. Okay, 0 to 100, or we can say 0 to 1. Okay, so depending on the value of S, so when the soil is completely saturated, so in that case your S value will be 1. Now what is the physical significance of this S? Already we have discussed in the previous problem that the definition of S is VW by VB. Now as you know that VB, this is basically summation of VW plus VA. Now when all the voids or all the pores which are basically inside the soil mass is filled out by water only, there is no air, then VB will be equals to VW. So that means VW by VW, that means S will be 1. So are you getting my point? So the physical significance of complete saturation is that all the pores are filled up by water only. Okay, so there is no air inside the soil mass. So in this way the value of S becomes 1. So in that case the gamma saturated, so you will be getting the unit weight as gamma saturated, so it will be GS plus E divided by 1 plus E multiplied by gamma W. Now the exact opposite scenario when the soil is completely dry. Okay, so this is one scenario. So these are two extreme circumstances. So when the S value is 1 and when the S value is 0. So when the soil is completely dry. Completely dry. Dry means there is no water inside the soil mass. So that means VW is your 0. So obviously S value will be 0. Okay. Since the definition of S is ratio of volume of water to volume of voids. So therefore your S value, this represents, this condition represents, condition 2 represents your S value equals to 0. So that means gamma dry would be GS, sorry, now this second component will be vanished from this equation, so only GS divided by 1 plus C into gamma W. So you have got gamma sat, you have got gamma dry. Now it becomes very simple. Okay, now what you have to do, you have to basically substitute, these values here. Okay, just let me add one slide here. Okay, so we can define the ratio now in this fashion, that gamma saturated by gamma dry equals to GS plus E divided by GS. Yes or no? If we divide this expression by this expression, then what will remain left? Yes, very good. So you have already got the answer. Okay. So now we'll substitute the values. So these values, this value is given as 2.65. Okay. And GS value is given as 2.65. Okay. No. Sorry. So this value is given as 1.5. The ratio of gamma sat to gamma dry is given as 1.5 and GS value is given as 2.65. So 2.65 plus E divided by 2.65 equals to 1.5. Now if you solve this equation, you will get the E value as, so how much you have got? 1.325. Okay, so this is the answer. So through this problem, we have seen when the ratio of saturated unit weight to dry unit weight is given, and in addition to that, the specific gravity of soil solids is also given, we can easily determine the void ratio of the soil. Okay. So now we'll take our third problem. So this is again taken from GATE examination 2013. So in this problem, it's mentioned that in its natural condition, a soil sample has a mass of 1.980 kg and a volume of 0.001 meter cube. After being completely dried in an oven, the mass of the sample is 1.800 kg. Specific gravity G is 2.7. Unit weight of water is 10 kilonewton per meter cube. The degree of saturation of the soil is. Okay, so lots of data are given to this problem. So first of all, the volume and mass of the soil sample in its natural condition are given. Okay, so we'll use the mass of the soil. So it will be designated by M. So it's given as 1.980 kg. Then the volume corresponding to the natural condition is given as 0.001 meter cube. Then when the soil is completely dried in an oven, the mass of the sample. So what is this mass? Can you please let me know? When a sample is completely dried in an oven, then the remaining mass of the sample, what is represented by that mass? Which component? As you know that the soil is a three-phase system. MD, exactly. So dry, that means we can also say MS, that is nothing but the mass of solids. So as you know that mass, this will also be contributed by three components. So air, water and solid. Now mass of air is very negligible compared to MW and MS, so we can neglect this part. So only MW and MS leaving behind. Now out of these two components, when you are basically drying a sample in an oven completely, okay, so then this MW will not be there, it will also become zero. So only MS will be there. So that means this mass is nothing but the mass of solids. Okay, so this is the trick here. So MS is 1.800 kg, and in addition to this information, the G value, that is the specific gravity of soil solids, is given as 2.7 and unit weight of water gamma W This is given as 10 kilonewton per meter cube. So you have to determine the degree of saturation, that is VW by VB. So this is the definition of degree of saturation. Okay. So S is nothing but VW by VB. So for that, we need to know the volume of water inside the soil sample and the volume of voids inside the soil sample. Now, how we can determine these two entities, the volume of water and the volume of voids? How we can determine? How we can determine these two volumes? Gamma D. Okay, you are saying by using the information of gamma D. I think you are approaching in the correct way. Okay. So first of all, we'll determine the volume of water. Okay, volume of water will determine. Now how we can determine the volume of water? Is it possible to determine the volume of water? Okay, so let me approach in this fashion. So first, let me determine the volume of solid. So volume of solid is nothing but mass of solid divided by the density of solid. Yes or no? Because density is nothing but mass by volume. So we can rewrite in this way. So volume of solid will be mass of, yes, so mass of solid divided by density of solid. Now the mass of solid is with us. This is 1.8 kg. Now what is about this density of solid, soil solids? So density of soil solids we can calculate, or we can get from this definition, that is specific gravity of soil solids. This is the ratio of rho S to rho W, density of soil solids to density of water. Now we know G, we know rho W, because G 2.7 for this problem. And what about rho W? This is 1 gram per centimeter cube. Yes or no? What is the what is the density of water? The density of water you can calculate from this unit weight, na? So it's unit weight. So if you divide the unit weight by acceleration due to gravity, that is G, you can easily determine the density of water. So for example, rho W, so this will be simply gamma W by G. Okay, so gamma W, it's given as 10,000 Newton per meter cube, and G, for simplicity, we are taking 10 meter per second square. So it will be 1000 kg per meter cube. Okay. So this is the value of rho W. Now we know rho W, we know G. So the rho S value would become 2.7 multiplied by 1000. That means 2700 kg per meter cube. So as we know rho S, so our next step will be to calculate the Vs. So Vs, it will be Ms by rho S. Now what is the value of Ms? 1.8 kg. And what is the value of rho S? 2700 kg per meter cube. So please calculate and tell me what would be the value of Vs. It will be 6.67 into 10 to the power minus 4. Yeah, very good. Meter cube. Okay. Now we know Vs. So we can calculate the value of Vb. How we can calculate the value of Vb? How? How we can calculate the value of Vb? So Vb will be simply V minus Vs. The total volume is Va plus Vw plus Vs. Now Va and Vw, so this is nothing but Vb. So Vb plus Vs. So Vs we know, so therefore Vb we can calculate by subtracting Vs from the total volume. Now what is the total volume? So the total volume is 0.001. That means 1 into 10 to the power minus 3 meter cube minus 6.67 into 10 to the power minus 4. That means 3.33 into 10 to the power minus 4 meter cube. So this is the value of Vb. Okay. Now what is the additional component we need to know? What is the additional component we need to know? Before calculating the degree of saturation of the soil. So we need to know the volume of water as well. So how we can calculate this volume of water? So we'll basically approach from this side, that mass, total mass, this is Ma plus Mw plus Ms. Now the mass of water we can neglect, mass of air we can neglect, so we can calculate the mass of water by subtracting the mass of soil solids from the total mass. That means mass in its natural condition. So what is the mass in its natural condition? 1.98. So 1.98 minus 1.8. So this is the mass of soil solids. Okay. So that means 0.18 kg. So therefore it becomes very easy to calculate the volume of water. It will be simply Mw by rho W. That means 0.18 divided by 1000. That means 1.8 into 10 to the power minus 4 meter cube. Okay, let me check whether yeah, so 1.8 into 10 to the power minus 4 meter cube. So therefore the degree of saturation of the given soil it would be 1.8 into 10 to the power minus 4 divided by 3.3 into 10 to the power minus 4. So approximately 0.54. That means 54%. This is the answer. So in this way, we can calculate the degree of saturation of a given soil sample when, yeah, okay. So can we solve this problem? Gamma D and AC equals to WG. Okay, so you are trying to say that we can solve this problem by utilizing this equation or this relationship as well. Yes, there are too many ways to solve a specific problem. So you can, but okay, can you please clarify a little bit that how you can calculate the degree of saturation? Okay, degree of saturation. I think here this void ratio then you need to know, and water content. Yeah, so you have to basically calculate two additional entities, that is void ratio and water content. So water content you can calculate, water content you can calculate from this ratio mw by ms. You know mw, this is 0.18 kg. You know ms, this is directly given to the given to us, that is 1.8 kg. So we can easily calculate the water content. Now coming to this void ratio, this would be vb by vs. So vs we have calculated as 6.67 into 10 to the power minus 4 meter cube, and vb 3.33 into 10 to the power minus 4 meter cube. So once these two entities are known to us, we can easily employ this type of relationship to calculate the degree of saturation of the given soil sample. But I think we can note one point here that uh, computationally, I think this type of approach will be little bit expensive. Okay, please check out. So otherwise, you can use any of these two approaches. Okay, but keeping in mind the time duration of an exam, so you have to mostly consider the way or approach which is basically computationally less expensive or computationally efficient. Okay, so any doubts with this problem? Okay, so then we can move further. So we'll take our problem 4. So in this problem, a sample of clay has the liquid limit and shrinkage limit of respectively 60 and 25%. If the sample has a volume of 10 ml at the liquid limit and a volume of 6.4 ml at the shrinkage limit, determine the specific gravity of the solids. So this is the three-phase representation of the soil sample corresponding to its liquid limit and shrinkage limit. Okay, so as you know that liquid limit, so the entire mass will be contributed by only mass of water and mass of solid. Okay, and for shrinkage limit, so this will be mass of water, mass of solid, and there will be some air, but as we are ignoring or neglecting the mass of air, because the mass of air is basically very less compared to mass of water and mass of solid. However, from the volume point of view, so you have to basically consider the volume of air as also for the shrinkage limit. Okay, so these are the two schematic representation of the basic three-phase relationship of the soil sample at liquid limit and shrinkage limit. And this limit are given as, so SL, we can summarize the data here. So SL, so first LL, liquid limit is given as 60% and shrinkage limit is given as 25%. Okay, and liquid limit, the volume V1, this is given as 10 ml, and the volume at the shrinkage limit given as 6.4 ml. Now we have to determine the specific gravity of the solids. Now first let me know, what do you understand by this limits, Atterberg limits? Okay, liquid limit and shrinkage limit. What is the definition of liquid limit and shrinkage limit? Any idea? What are these limits? Okay, so I think you all are familiar with this type of, yeah, LL at which water flow by a liquid. Okay, I think it's okay, but more elaborate explanation or discussion on this matter. Okay, I think uh, it will help you, this schematic. So this is the volume along y-axis, and this is the water content. Okay. Now, if you observe the typical behavior of a soil, means considering these two aspects, that is volume versus water content, then you will see something, this kind of behavior. Yes or no? So volume will vary with water content in this fashion. Now, this behavior can be grouped or can be categorized into different zones. Okay, so suppose this is one zone, this is one zone, and this is one zone. Now, what is the significance of this behavior? That if you reduce the water content, your volume will also go on decreasing. So if you reduce the water content, your volume accordingly will reduce. So this behavior is basically indicating that physical meaning, or conveying that behavior of the soil, that if you reduce water content, your volume will also reduce. But after a particular or a certain value of water content, as you are decreasing the water content, after a particular limit, there will be no such variation in the volume. That means volume becomes constant. So that limit is called shrinkage limit. Okay, so again this zone are basically named as, so this is the solid phase, this is the semi solid phase, this is the plastic phase, and this is the liquid phase. Okay, so as if these limits are boundary between two phases. So shrinkage limit, this is the boundary between solid and semi solid phases. Then plastic limit, so this is the boundary between plastic and semi solid phases. Then liquid limit, this is the boundary between liquid limit, this is the boundary between liquid and plastic phases. Okay, so in this way the Atterberg limits are basically defined. So these limits are basically used to identify the consistency of a soil mass. I hope you all are familiar with these terms. Okay, now up to this shrinkage limit, what will happen in the degree of saturation of the soil mass? Any idea? Up to the shrinkage limit, starting from liquid limit to shrinkage limit, what would be the value of degree of saturation of the soil mass? Any idea? Okay, so we'll come to that point later. First, uh, we'll start with the definition of water content. So I think for this time being, it's clear that these limits are nothing but the water content of a soil sample corresponding to different consistency. Is it clear? So these limits are nothing but the water content of the soil sample. है ना? So this is in the x-axis, this is water content. So these limit are nothing but the water content. So the water content at which the soil consistency basically changes from liquid phase to plastic phase. That is called liquid limit. Now what is plastic limit? So this is the water content at which the consistency changes from plastic phase to semi-solid phase. What is shrinkage limit? The water content at which the consistency changes from semi-solid phase to solid phase. So that means these limits are nothing but water content of the soil sample. So we'll first define the mass of soil solids. Mass of soil solids as ms. Okay, in this clay soil sample is nothing but ms. Okay, so as shown in this representation, and you know this mass will not change. The mass of soil solids will not change. So as you are decreasing the water content, mass of water will change. Decreasing water content means what? The water content, this is basically mass of water to mass of solid. So you are decreasing the water content. That means you are decreasing the mass of water, not the mass of solid. Okay, so please keep in mind. So mass of solid will be constant. So only mass of water is basically changing from one Atterberg limit to another Atterberg limit. Okay, and we can calculate this mass of water if we know the this Atterberg limits. So this is ms. Okay, we are basically denoting the mass of soil solids in the given clay sample as ms. Now what will be the mass of water at liquid limit? What will be the mass of water at liquid limit? Yeah. No, I don't think that. Okay, so at LL, at liquid limit, the mass of water, if we denote it by mw, so it will be nothing but what? 0.6 times ms. Now you may raise the question, how we can write this mw1 as 0.6 times ms? It will be highest. Okay, so I got your point. The mass of water will be at its highest value compared to other limits, shrinkage limit and the plastic limit. But the value would become 0.6 times ms. How? Because this LL is nothing but water content, and from the basic definition it is mw1 divided by ms. The mass of water divided by mass of solid. Mass of water divided by mass of solids. So mw1 becomes ms multiplied by 0.6. Okay, I hope you got the point. Okay. Similarly, tell me what should be the mass of water at shrinkage limit? What should be the mass of water? Yeah, exactly. So 0.25 times ms, because this 25%, this is nothing but mw2 divided by ms. Now please observe very carefully. So this is the reduction in the mass of water when the consistency of the soil is basically changing from liquid limit to shrinkage limit. So when we are at liquid limit, the mass of water was mw1, but when we reach the condition, reach shrinkage limit, the mass of water becomes mw2. So this mass reduction basically happens inside the soil sample by delta mw. Okay, so delta mw, therefore delta mw, we can write it as mw1 minus mw2. Now what is mw1? 0.6 times ms. And what is mw2? 0.25 times ms. Means finally 0.35 times ms. So this is the reduction in water, mass of water. Okay, so this is the reduction in mass of water. Yeah. Now we know another information. What is that information? That at liquid limit the total volume was 10 ml, and at shrinkage limit the total volume reduced. It is basically, it reduces to 6.4 ml. So that means what is the change in volume happens here? What is the change in volume? Total volume. The change in total volume is nothing but 10 minus 6.4. So V1 minus V2. Okay. So it would be V1 minus V2. That means 10 minus 6.4. That means 3.67. Now, this is the reduction in total volume. Now, what would be the reduction in only volume of water? Will it be same to the reduction in total volume? And if so, why? Whatever reduction is basically occurring in the total volume, so that will be solely contributed by the reduction in the volume of water or not? What do you think? Okay, so for that, you need to know what is the degree of saturation of the soil up to shrinkage limit. So please keep in mind that up to shrinkage limit means starting from the liquid limit to shrinkage limit, the soil will be under complete saturation. Now what does it indicate? If the soil is under complete saturation, that means the pores are completely filled up by water only, no air inside the soil pores. Now if the pores are completely filled up by water only, then whatever change is basically happening, that is due to only the change in volume of water. Okay, so this is the conclusion. So that means this delta VW will be nothing but 3.6 ml. The same means the entire change is basically contributed by the volume of water. Water means only, not no air. Why? Because the soil is under complete saturation. And this is up to shrinkage limit. So if you reduce the water content beyond shrinkage limit, then the soil sample will be no more under complete saturation. The soil will be the degree of saturation will start reducing and it will be under unsaturated or partially saturated condition. However, starting from LL to SL, this will be under complete saturation. So therefore, delta VW we have got, this is as 3.6 ml. Now, if we know delta VW, then we can easily calculate the delta MW value. How? So it will be delta VW multiplied by rho W, volume into density. Density we know 1 gram per cc. Delta VW we know 3.6. So it will simply becomes 3.6 gram. So delta MW we have got 3.6 gram. Okay. So from this equation, suppose this is equation 1 and this is equation 2. So from equation 1 we are getting delta MW value as 0.35 ms, and from equation 2 we are getting delta MW 3.6 gram. So we can equate these two equations and we can easily calculate, okay, the value of mass of soil solids, that is ms. So equating equation 1 and 2, you can get the mass of solids as 3.6 divided by 0.35. So what would be the value? 10.29. Very good. 10.29. Okay. So this is the mass of soil solids. Now what we have to determine? We have to determine the GS. That means specific gravity of soil solids. Now what is the definition of specific gravity of soil solids? This is nothing but rho S by rho W. Density of soil solids to density of water. So this is the ratio of density of soil solids to density of water. Again, this rho S, so this will be ms by Vs, mass of solid by volume of solid, and rho W we know 1 gram per cc. So that means this is the critical parameter which we need to know before calculating the value of GS, that is rho S. Now for calculating rho S, we already know the value of ms, that is 10.29 gram, but we don't know the value of Vs, that means volume of soil solids. So how we can determine the volume of soil solids? So to know the volume of soil solids, you need to consider any of these two conditions, any of these two Atterberg limits, either liquid limit or shrinkage limit. How that we'll see. So you know the total volume corresponding to each of these limits, that is liquid limit or shrinkage limit. So let us consider the liquid limit case. Okay, so let us consider the liquid limit. So the total volume is 10 ml. So you need to know the Vs value. So to know the Vs value, you need to know Vb, because Vs, this will be nothing but total volume V1 minus Vb, or you can say Vb1. Okay. Now what is Vb1? So Vb1 is nothing but Vw1. Why? Because the soil is completely saturated. The soil is completely saturated. So hence this information is very, very critical or essential for us. If we don't know, then we can write this equation that Vb1 equals to Vw1, because as you know, in the general scenario, that volume of wires, this is summation of volume of water and volume of air. But since here the soil is completely saturated, so we can easily write BB1 equals to BW1. There is no volume of air inside the pores. Okay, no air inside the pores. Now how we can determine this BW1? So BW1 we can determine MW1 by rho W, mass of water at liquid limit divided by density of water. Now how we can know the mass of water at liquid limit? So it will be nothing but 0.6 times ms. Already we have written na that MW1 is nothing but 0.6 times ms. So that means 0.6 multiplied by 10.29 divided by 1. So what would be the value? 6.17 ml. So this is the volume of water, or rather we can say volume of voids. Sorry, volume of water. So therefore we can calculate the volume of solid by subtracting the 6.17 from the total volume, that is 10. So that means this value would be 3.83 ml. Now if we know Vs, we can calculate the rho s value, ms by Vs, ms by Vs, that means 10.29 divided by 3.83. So 10.29 divided by 3.83, 2.68 or 69. So therefore GS would be rho s by rho W. So 2.69 divided by 1. So this is the so 6.17. So this is the volume of water at liquid limit. So the volume of solid will be 10 minus 6.17, that is 3.83 ml. So rho s would be ms by Vs, that is 2.69. So GS would be rho s by rho W. So it's again 2.69. Now you can ask me why we are considering only the liquid limit condition. So it's my suggestion that you please consider the second condition as well, that is the shrinkage limit. So we'll again end up with the similar result. So if you consider the shrinkage limit case, so the total volume will be different. So the total volume will be 6.4 ml for the shrinkage limit case. So accordingly, you will get a different, accordingly you will get a different volume of water. Okay, so volume of, please keep in mind that volume of solid will not change. So it's constant. The solid component will not change. Mass of solid as well as volume of solid, it will remain same. Only this total volume and the volume of water will change, because for shrinkage limit this will be 0.25 times ms. So here you will be getting a different value. Now this value you have to subtract from the from 6.4, not from 10. Okay, so then you will be getting again the volume of solid at 3.83. You can check it. You can check it at your own. So ultimately you will be getting the same result, that is the specific gravity of solids at 2.69. Is it fine? Is it fine? Only you need to know the fundamentals, that is what would be the degree of saturation for all these limits, then the definition of water content, definition of specific gravity of soil solids. Okay, so these things you need to know. Okay, so hope seems to be these things seem to be fine from your end as well. So we'll take the last problem for this session. Okay, so this is a quite lengthy problem, so please be with me. So this is related to the grain size distribution. So first we'll read the problem statement, what is basically given to this problem. So where 500 gram of soil taken from Kanpur, Uttar Pradesh were brought to a soil lab for testing of grain size distribution. The weight and number of each sieve for sieve analysis is given in table 1. So this table 1 basically gives the sieve size and the corresponding weight. So these are the series of sieves which are basically used in the sieve analysis. Okay, so for starting from 4.75 millimeter to 0.075 millimeter, and these are the corresponding sieve weight. In addition to that, the pan weight is also given. I know, I hope that you know about the procedure, the standard procedure by which this type of sieve analysis is basically performed. Otherwise, we will basically discuss while solving the problem. Okay. Now, in the second part, after the sieve analysis, the weight of each sieve along with soil is given in table 2. It is to be noted here that during sieving, a small fraction of the sample taken was lost as dust. Okay. So in the table 1, only the sieve weight is given. However, for table 2, sieve plus the soil, which is basically accumulated or retained on a particular sieve, that is also given. So that means sieve plus soil weight. This is given in table 2. Now coming to the third part, a hydrometer analysis was performed on the same soil by taking 40 gram of sample retained in pan. The hydrometer immersed in a soil solution of 1000 ml was read at specific timings as given in table 3. So the beginning portion was about the sieve analysis, and this portion talks about the hydrometer analysis. Now, why can you please let me know why these two different things are needed? Means for some cases hydrometer, for some cases the sieve analysis. What is the fundamental difference between these two analyses? Any idea? Or we can frame the question in a different way, that when this sieve analysis is performed and when the hydrometer analysis is performed or needed. Okay, so when particles are less than 0.25, 0.25 or something else. Okay, so I think this hydrometer analysis is basically performed for finer fraction of the soil sample, है ना? So finer fraction means the portion which passes through the 75 micron sieve. That means 75 mm, 0.05 mm sieve. So the portion which is basically retained on the pan. Here it's mentioned na, that a hydrometer analysis was performed on the same soil by taking 40 gram of the sample retained in pan. Now, what portion retained on pan? The portion which basically passes through 75 micron sieve. Okay, so that means this hydrometer analysis is basically performed on the finer fraction, finer portion which passes through the 75 micron sieve. And these are the readings from the hydrometer analysis. So in one column, so the time, and in the second column the corresponding readings are basically given. Now the calibrations correspond to 3. as 20 centimeter and 24 as 7.5 centimeter effective depth. The viscosity of water is 8.9 into 10 to the power minus 7 kilonewton second per meter square. The soil solution temperature was at 32 degrees centigrade. The meniscus correction is 0.5 and the combined dispersing agent and temperature corrections was observed to be minus 2.1 for the hydrometer. Specific gravity of soil particles was found out to be 2.67 from experiment, and the formula for diameter and percentage finer for hydrometer analysis is given below. So this entire part is basically related to hydrometer analysis procedure. Okay, so when we'll be calculating the means diameter and the percentage finer corresponding to hydrometer readings, then we need this type of data. We'll see. So now, depending or based on the data which are given to this problem, we have to answer these two questions. So first of all, what type of soil is it? So whether it's high plasticity silt or low plasticity silt or silty sand, or we can't say. Okay, so we have to answer out of these four options. And secondly, according to the coefficient of curvature and coefficient of uniformity, the soil can be classified as well graded, option 2 uniformly graded, option 3 gap graded, and option 4 difficult to say from the given data. So these two questions are framed based on the data given to this problem. Now I hope so this part is not covered completely. Okay, so from this week, that is week 2, we'll be learning about this classification of soil. So that's why we'll be answering these two questions in the next week. But before that, whatever calculation is needed to answer this type of questions, that is already known to us. Okay, we are familiar with that calculation. Means how to plot the grain size distribution curve, or how to calculate the percentage finer corresponding to a particular sieve size or particular diameter or particle size from the hydrometer analysis, that we know. So therefore, in this session, we'll be restraining ourselves only to the calculation portion. Okay, and we'll be answering these two questions in the next session, in the upcoming session. Okay, since the classification system is not completely covered, so we are still learning the classification, different type of soil classification systems, or how a soil sample is basically classified. Okay, so before proceeding further, so we'll start with very fundamental. So first of all, this table 1 is basically giving the sieve weight, and table 2 is giving the sieve plus soil weight. So we can easily determine how much soil is basically retained on a particular sieve. By how? By deducting these two components, means deducting this sieve weight from the sieve plus soil weight component. Is it fine? So if we deduct the sieve weight from this weight, that is sieve plus soil weight, we can easily calculate how much soil is retained on a particular sieve size. I think it's okay. Okay. Now, by knowing how much soil is basically retained on a particular sieve, we can again calculate. So what are the things we will be calculating? So here I am summarizing. So first, sieve analysis. Okay, so first we will be concentrating on the sieve analysis part. So first we can calculate the soil weight retained on a sieve, and we can calculate this entity by deducting the sieve weight from the combined sieve plus soil weight. Okay. Second, cumulative soil weight. Cumulative soil weight retained on a sieve. Now how we can calculate? By adding the soils which are retained on the coarser sieves. Okay, so that will give you the cumulative soil weight retained on that sieve. That we'll see through the while we'll be solving the problems. Then next we'll be calculating the percentage finer for a sieve size. Okay, so okay, before calculating this percentage finer, we need to calculate the percentage cumulative weight, means with respect to the total. Percentage cumulative soil weight retained on a sieve, and finally percentage finer for a sieve size. So these are the 4 basic details which we need to know before moving further, that is before going to the hydrometer analysis part. Okay, so these are the 4 basic details which are required for the sieve analysis part. So this is the table. So in this table, so the first column, it tells about the sieve size in millimeter. Then this is the second column. Here the sieve weight is basically given in gram, and this is the third column where combined sieve plus soil weight is basically given. Okay, so this data are basically given from data are basically taken from table 1 and table 2. So these two tables, table 1 and table 2. Okay, so for your easy reference, I'm writing here. So this second column is basically taken from table 1, and this third column, this is taken from table 2. Now, as we discussed earlier, that we'll first calculate the weight of soil retained for each sieve, starting from 4.75 mm size to 0.075 and the pan as well. Now, how we can do that? We can do that by subtracting the sieve weight from the combined sieve plus soil weight. So please subtract the sieve weight from the combined sieve plus soil weight and let me know what are the values you are getting for the fourth column. So since it's a quite lengthy problems, okay, so please do the calculation a little bit faster. So what are the values you are getting for the fourth column of this table? So it will be 236 minus 236.29 minus 230.67. Okay, so for a sample calculation, for the first entity in column 4, so 236.29, or rather this is the sample calculation. I can write okay 4.75 in sieve size. So column 4, so that will be 236.29 minus the sieve weight is 230.67. So how much it is? 236.29 minus 230.67. So that means 5.62. So this value would be 5.62. Okay. So similarly for other sieve sizes also we can calculate the weight of soil retained on that particular sieve. So I have already calculated this part, so I am writing from there. Okay, so you can calculate at your own and let me know if you face any difficulty for the calculation portion. Okay, so I think there should not be any difficulty, at least for this part. So it's simple subtraction. Subtraction means column 3 minus column 2. So in this way you can get column 4. So 5.62, then 20.37, then 57.11, then 65.35, then 77.03, okay, then 68.93, 45.42, 50.36, and finally 105.2. So these are the weight of soil retained on corresponding sieve. Means 5.62 gram soil is retained on 4.75 mm sieve size. 50.36 gram of soil, total soil out of 500 gram is retained on 75 micron sieve. Okay. So total 500 gram of soil basically taken from this for this analysis, sieve analysis, and out of this 500 gram, so these are the distribution or these are the fractions which are basically retained on this sieve sizes starting from 4.75 to 0.075 mm. Now what is the cumulative weight? So cumulative weight is basically, this is the addition of the weight component, the retained weight component that is coarser than the considered sieve size. Suppose if you consider the sieve size of 4.75 mm, so before this sieve size there is no coarser sieve size we have considered, at least for this analysis or for this problem. So that means the cumulative component will be simply 5.62. Now if we come to the second sieve size, that is 2 mm. So before 2 mm there is another coarser fraction. As you know that when sieve analysis is basically performed, so there is a stacking of sieves. Okay, series of sieves are basically stacked one by one. So the top one is the coarser fraction. Then in this way, the finer sieve is basically stacked at the bottom of this series. Now at this level, suppose level 2, what are the cumulative weight? So cumulative weight would be the weight retained on this particular sieve plus the weight retained coarser than the sieves, coarser than that the particular sieve size. So right now we are considering 2 mm sieve size. So there is only 4.7 mm sieve size which is basically coarser than this sieve size 2 mm. So the cumulative weight will be addition of these two components, addition of 4.75 and 2. Is it fine? Are you getting my point? So how we are calculating cumulative weight component for a particular sieve size? Okay. So 5.62. Now for 2 mm. So then let me know what would be the value for 2 mm. What would be the cumulative weight retained on 2 mm sieve size? Then it will be more clear whether, yeah, very good, 25.99. So the value would be 25.99. So it will be 25.99. So in this fashion, okay, so 77.48. How you are getting 77.48? Oh, sorry. You are doing one mistake. So for 1 mm ship size, not only these two, you have to add this at as well, na? Because 4 mm for one, two is coarser than one. At the same time, 4.75 is also coarser than one, na? So you have to basically add all these three components. So therefore, for 1 mm ship size, the cumulative weight retained will be 83.1. Okay. Okay. So similarly, I am writing here. So 148.45, then 225.48, then 294.41, 339.83, then 390.19, and finally 495.39. Okay, so I can do mistake, please cross check all these values. So in this way we have got the fifth column, that is the cumulative weight retained on each ship, starting from 4.75 mm to 0.075 mm. Now can you please clarify one thing? We have taken 500 gram, the total sample mass or the total weight of the sample was 500 gram, but we have ended up with 495.39 gram. So there is a discrepancy. By how much? So 500 minus 495.39. So that means 4.61. 4.61 is lost out of total 500 gram. Now what can be the possible reason behind this discrepancy? Why we are not getting exactly 500 gram of soil sample which we have taken at the beginning of this test? This is, you are saying that this is retained. No, that is not a logical answer. So this is retained in sheep parts because when you are basically taking the weight of sheep plus soil weight, that should come out, or that should come out in that figure, means in third column. You are basically taking the weight including the sheep plus soil weight. So whatever component or fraction which are basically retained on the sheep part, that should be reflected in the third column. Any other reason by which we can lose this 4.61 component, 4.61 gram out of total 500 gram? I think this is already mentioned in the problem statement itself. So it's mentioned that it is to be noted here that during sieving, a small fraction of the sample taken was lost as dust. Okay, so this is the possible reason behind this kind of discrepancy, that a small fraction is basically was lost as dust, and that weight we cannot reflect in the actual readings which we have taken from the analysis. Okay, so therefore we have got the weight of soil retained, and we have got the cumulative weight of soil retained for each ships which are used in this analysis. Now we will be calculating the percentage weight retained, that means with respect to the total weight. So with respect to 500, how much percentage is basically retained on a particular ship? So it is also very straightforward. So column 5, so it will be simply 5.62 at least for 4.75 mm. For column 6, this will be 5.62 multiplied by 100 divided by 500. So this is the percentage, cumulative percentage retained on 4.75 mm shape. Okay, so 5.62 divided by 5, so it will give you 1.12%. So in this way you can calculate for all other ship sizes. means 2 mm, so it will be 25.99 into 100 divided by 500. So 25.99 divided by 5, so it will give you 5.20. Okay, so the first one is 1.12, then 5.20. So I am writing the other values here, so please cross check these values. Okay, so 16.62, this is for 1 mm ship size, then 29.69, then 45.10, 58.88, 67.97, 78.04, and 99.08. So in this case also we are not getting exactly 100. Okay, since a small fraction was lost due to or as a dust. Okay, so this is for percentage cumulative weight retained. So here you should correct it, percentage cumulative weight retained. Now what would be the percentage finer then for a particular ship size? So it will be, so it is basically retained. Now what is passing through that ship size then? So 100 minus this value, each of this value will basically indicate the corresponding percentage finer. So please keep in mind that these percentages are basically retained on that ship, on that particular ship. So if you subtract this percentage cumulative weight retained from 100, then you will be getting the percentage finer relevant to that particular ship which you are basically considering. Okay, so for sample calculation, this column 7, so it will be 100 minus 1.18, so that means 98.88. Okay, so 98.88 percentage, basically this percent of the total soil weight is basically passing through 4.75 mm ship size. So I am writing the other values here. So 94.80, this is for 2 mm, then 83.38, then 70.31, 54.90, 41.12, 32.03, then 21.96, and finally 0.92. Okay, so with this table is basically complete. So at the very beginning, means in the first column you are having the ship size, and at the end, means corresponding to column number 7, you are having the corresponding percentage finer. Now this is for the sieve analysis part. So we have to now calculate this type of data, means particle size versus percentage finer, for the hydrometer analysis as well. Otherwise the grain size distribution curve will be incomplete. So for getting a complete grain size distribution curve, now we have to basically proceed for the hydrometer analysis part. Okay, okay, so just let me come back to the the data point which we have got from this hydrometer analysis part. So in the first column we have got we are having the time, and in the second column we are having the corresponding hydrometer readings. Now a few points to be noted here, that when we will be basically considering this data, so a few things you should keep in mind, that first of all, you have to calibrate the hydrometer. Okay, calibrate the hydrometer. Right now I am not going into the details of the physical description of the hydrometer, how it works, means its working principle. Okay, so since this is basically dedicated only or means specifically for the problem solving part, so I will be mainly emphasizing on the problem solving part. Okay, so this all these details you can get from the lecture videos or the lecture materials which are uploaded on the course website. Okay, so please go through those materials. So to get the particle size versus percentage finer data, you have to first calibrate the hydrometer. Now, what does it indicate? What is the physical significance of this kind of calibration of a hydrometer? So calibration of a hydrometer represents that these are the raw data. Okay, so you can say these are the RH values, time versus RH. Now, what is the working principle? Okay, so for this time being, we can discuss a little bit about the working principle of a hydrometer. So what is the working principle of a hydrometer? Can you please let me know? What is the working principle of a hydrometer? Any idea? Do you have any idea about the working principle of a hydrometer? How it works? Okay, so you are in the right track. That means you are trying to say that uh, soil particles. Okay, okay. Someone is saying that can you make a small recap for this problem from the first, because I joined lately. I don't know to do the initial steps. Okay. So for those who basically came late, so I am basically repeating the problem statement once. Okay. So first of all, for the specific problem, problem 5, what we are doing, we are given basically some data corresponding to sieve analysis and as well as hydrometer analysis. Okay, so 500 gram of soil taken from Kanpur, Uttar Pradesh were brought to a soil lab for testing of grain size distribution. The weight and number of each sieve for sieve analysis is given in this table. Now in table 2, after the sieve analysis, the weight of each sieve along with the soil is given in table 2. Okay, so in this table, you are having the sieve weight plus the soil weight, which are basically accumulating or which is basically retained on that sieve. And this is the additional statement. uh, we have basically discussed about it, about this statement, that it is to be noted here that during sieving a small fraction of the sample taken was lost as dust. Now coming to the third portion, so a hydrometer analysis was performed on the same soil by taking 40 gram of the sample retained on pan. The hydrometer immersed in a solid solution of 1000 ml was read at specific timings as given in table 3. So these are the hydrometer analysis data basically, which we are currently dealing with. And these are the few basic information which we should require, means for basically for having the particle size versus the percentage finer distribution related to the hydrometer analysis. Okay, that we'll see. And these are the two questions related to this problem. Means given the data in problem 5, we have to address what type of soil is it, whether it is high plasticity silt, low plasticity silt, silty sand, or we can't say. And secondly, according to the coefficient of curvature and coefficient of uniformity, the soil can be classified as well graded, uniformly graded, gap graded, or difficult to say from the given data. So these are the two questions, and we have discussed earlier that since the soil classification system is not covered completely as of now, so we'll be basically limiting or restraining ourselves for this session only to the calculation part, and we'll basically address these two questions in the upcoming or next session. Okay, So for that already we have basically completed the sieve analysis calculation part. Okay, so this is the complete calculation as you can see from this slide. So this is a table where you can have the sieve size, the corresponding sieve weight, the corresponding sieve plus soil weight, the weight of soil retained on that sieve, cumulative weight retained on that sieve, percentage cumulative weight retained on that sieve, and the percentage finer for that specific sieve size. Okay, so these are the calculation, or this is the calculation related to only the sieve analysis part. So from this calculation you can have a grain size distribution between sieve size and the percentage finer up to, means from 4.75 mm up to 0.075 mm. Now a soil which is having particles lesser than 0.075, obviously it can have, soil can have particles ranging from some particle size 4.75, even more than 4.75, to some fraction lesser than, even lesser than 0.05 mm. But please keep in mind that from the sieve analysis data we can get the distribution of the particle size only within these limits, 4.75 to 0.075. Now what is for the remaining part, means the finer fraction, the finer which is basically the fraction which is basically finer than the 0.075 mm. So for that this hydrometer analysis is basically additionally performed. Hydrometer analysis basically additionally performed on the same soil by taking 40 gram of sample retained in pan. Retained in pan indicates that the portion which is basically finer than the 0.075 mm. Okay, 0.075 mm. Now on this fraction, or on this 40 gram of soil sample, we have basically performed the hydrometer analysis, and the data which are basically taken from this test are basically given in table 3. Now we were discussing about the calculation, means based on this data. Okay, so for this calculation, this type of calculation, first we have to calibrate the hydrometer, because our ultimately our target is to determine the particle size versus percentage finer. So this is our motive, because anyhow you need to plot the percentage finer in the y-axis, and this is the particle size or particle size distribution, suppose in millimeter. And this type of plot is basically known as, or you can GSD, grain size distribution curve. Okay, this type of plot is basically known as grain size distribution curve, and it is very very essential for classifying a given soil sample, or to calculate the percentage of these fractions. Mean how much amount of sand is present inside the soil sample, how much amount of coarser sand or silt is present, clay, then clay fraction is present. Okay, so these are the constituents of a soil, means gravel, then sand, then clay, then silt. Okay, so after performing this type of test we will be able to determine the relative or the respective fraction of these ingredients of a soil sample. How much percentage of gravel is present in the soil, sand is present, clay is present, silt is present. Okay, so for that we need to know the range of the particle size for this type of ingredients inside the soil. So for example, what is the size of sand? So the size of sand is basically varying from 4.75, so 0.075 mm to 4.75 mm. Then clay 0.002 mm to 0.075. Then for clay it's less than 0.002. So these topics, this is basically pertaining to the contents of week 2, so that's why we are not discussing it in much detail about these topics. Okay, so I would like to request all of you, please go through all the lecture contents or the videos, materials, whatever are uploaded on the course portal regularly, on a regular basis. Okay, so then you can have a clear idea about this aspect, and we'll basically address the questions framed for the specific problem in the next week. But for this time being, we'll be having the calculation part at least complete. Okay, so first we have to calibrate the hydrometer. Now as one of you answered that about the working principle of this hydrometer, that uh, soil particles from the speed at which they settle in suspension, okay, Stokes law. It's very correct that the working principle of the hydrometer is entirely based on the Stokes law. So where what is basically happened that after making the solution or suspension, whatever you can say, so this 1000 ml soil solution, so this is the container, suppose, and this is the 1000 ml soil solution where 40 gram of soil solids is basically mixed. Okay, then you are basically immersing the hydrometer. Okay, so my drawing is not very good. You are immersing the hydrometer and you are basically getting the reading for different time intervals. Okay, so here the time intervals are basically given in first column of this table 3, 0.5, 2 minutes, 10 minutes, 30 minutes, 120, 480, up to 1440 minutes. You are basically having the reading. Now what will happen here? So as the time elapses, the coarser particle which are basically present, relatively coarser particle which are basically present in the soil suspension, that will basically settle. Okay, and employing the formula or the fundamentals of Stokes law, we can easily calculate that how much percentage of this fraction is basically present inside the soil sample. Now for that we first of all need to know, or we first of all need to do a calibration of the hydrometer, because this calibration of the hydrometer will basically help you in getting the effective depth of the hydrometer related to a specific time window. Suppose we are interested to get the effective depth of the hydrometer at time 2 minutes. Okay, then how we can determine? So this calibration will help you for that part. Okay, how that we'll see. So these are the two formulas which are also given to this problem statement, that the D, that is the particle size diameter, you can get from this equation, and again this is based on Stokes law as you have basically written in the chat box, and this is the corresponding percentage final. Okay, so if suppose this D diameter is your 0.001 mm and this N is your suppose 20%, that means it indicates 20% of the total mass, the sample which we have taken for this kind of test is basically finer than this particle size. So 20% of the particle will be finer than this size. Okay, so these are the physical significance of this data which will be basically having after the calculation. Now if you observe very carefully, so to get the particle size, what are the information we need to know? First of all, the viscosity, eta means viscosity. Okay, so here I am writing, we need to know the viscosity of water. Viscosity of water, because this is the medium through which the particles are settling. Okay, so viscosity of water is given as 8.9 into 10 to the power minus 7 kilonewton second per meter square. Okay, so this is the viscosity of water. Now second, gamma S and gamma W. Now what is gamma S and gamma W? Gamma S, this is the unit weight of soil solids, and gamma W, this is unit weight of water. Okay, then what is HE? HE, this is the effective depth which I was talking about. Okay, this is, and T, this is the time. And coming to the second equation, this GS, this is the specific gravity of solids, and RC, this is the corrected hydrometer reading. Okay, we'll come to this topic. Okay, corrected hydrometer reading. And W, this is the weight of solids per, okay, so for 1 or per ml solution. Okay, per unit solution or per ml solution. Okay, so at the same time, I would request you that you please be careful about the unit systems which are basically involved in this type of equation. Okay, so that are also very, very essential. Otherwise, you will be ending up with wrong answers or incorrect estimate of the particle size and as well as the percentage final. Now, first, as I discussed, that first we need to calibrate the hydrometer. Now, how we can calibrate the hydrometer? So, for calibration, either you can calibrate the hydrometer from the basic principle, that is the volume of the hydrometer, the cross-sectional area of the bulb, okay, something like that. Otherwise, there are some standard figures in the textbook by which you can calibrate the hydrometer. Means calibration is nothing but the relationship between the reading which you are getting from the hydrometer test and the effective depth. Okay, so calibration, so this is basically establishing a relationship between hydrometer reading and effective depth. Okay, now what is the effective depth? Effective depth is the distance from the surface of suspension to the distance where basically the density of the suspension is basically measured. So as you can see, suppose this is the surface of the suspension and this is the point where this is the center of the bulb. So this distance is basically effective depth H. Now once you have the once you know the calibrated data or the calibration of the calibration plot of the specific hydrometer, then you can easily relate the hydrometer reading to the effective depth, okay, for different time intervals, means starting from 0.5 minutes to 1440 minutes. Okay, now before going into this part, this aspect, calibration of the hydrometer, you have to correct the hydrometer readings. So why you have to basically correct the hydrometer readings? What are the different types of corrections? Do you know? For a hydrometer test, you need to apply before going into the calibration part. Any idea? Meniscus correction. Yeah, very good. So this is one type of correction. And okay, so as a whole there are three types of corrections which you need to implement. Okay, so before going into this calibration aspect, so I am writing here about the different types of hydrometer corrections. So first of all, meniscus correction. Then temperature correction. Okay, because you are performing the experiment at the room temperature. Now the calibration is basically done for some another temperature. Now depending on the difference between this calibration temperature and the room temperature, mean the experiment temperature, you have to basically implement the temperature correction. Now for this time being, the soil solution temperature was 32 degrees centigrade. However, the hydrometer was basically calibrated at some different temperature. So for that you have to apply this temperature correction as well. Okay, so I will not be going into much details about this type of correction. So for that, please go through the lecture materials or lecture videos or any standard textbook. You can have an idea about this type of corrections. And lastly, the dispersing agent correction. Okay, dispersing agent correction. Now besides knowing this type of corrections, you have to also keep in mind what is the nature of this type of correction. Means meniscus correction, is it positive or negative in nature? Temperature correction, is it positive or negative? Dispersing agent, is it positive or negative? So meniscus correction is always positive. So you have to add, to get the corrected hydrometer reading, you have to add this correction factor to the raw hydrometer reading data. Temperature, it depends. So if the test temperature is greater than the calibrated temperature, then I think you have to add, otherwise you have to subtract. And dispersing agent correction is always negative. Okay, now we'll see what information is given in the problem statement itself. So in the problem statement, the meniscus correction is given as 0.5. Okay, positive. And the combined dispersing agent and temperature correction is given as minus 2.1. So instead of giving the correction factor individually, so the combined temperature and dispersing agent correction was given as minus 2.1. Now what would be the corrected, then what would be the corrected hydrometer reading? So suppose RH, so this is the raw hydrometer reading data. Okay, so this is raw data. And RC, so this is the corrected one. So RC, this will be RH plus CM plus minus CT minus CT. Now CM stands for meniscus correction, CT stands for temperature correction, and CD stands for dispersing agent correction. Now for this specific problem, CM is given as 0.5 and combined these two is given as minus 2.1. So finally RC becomes RH minus 1.6. Okay, so this is the relationship between the raw hydrometer data and the corrected hydrometer data. Okay, so in this way you can correct the hydrometer data from the raw data after implementing three types of corrections: meniscus, dispersing agent, and the temperature correction. Okay, now we'll use this table. So first of all, in first column, the time intervals are basically noted, and then in the second column, the raw hydrometer reading, and the third column, we'll be calculating the corrected hydrometer reading. Now, please let me know what would be the corrected hydrometer reading corresponding to time 0.5 minute. So RC is basically equals to RH minus 1.6, na? So we have to subtract 1.6 from each of this data. So 24 minus 1.6. What would be the value? 22.4. Then 18. Then 13. Okay. Then 9.3. Then 6.8. Then 7.9. Then 5.2, and then 2.7. Okay, now in this way we have got the corrected hydrometer reading. Now how we can get the effective depth? Now for that we have to go for the calibration aspect. So for calibration, a statement is given in this problem statement that the calibrations correspond to 3 as 20 centimeter and 24 as 7.5 centimeter effective depth. What is the meaning of this statement? The meaning of this statement is like that this is the RC and this is the HE. Okay, so when the hydrometer is calibrated like that when the RC is 3, it indicates an effective depth of 20 centimeter. Okay, so 20, and when the corrected hydrometer reading is 24, it indicates an effective depth of 7.5. So 24, 7.5. Now this in between 3 and 24, for all the data in between 3 and 24, you can get the effective depth, corresponding effective depth by a linear interpolation. Okay, how? We'll see. Suppose for example we'll take the case of 0.5 minute, that is 22.4. Now what would be the effective depth? So 22.4. so first of all, this RC equals to 22.4. this effective depth would be 20 minus 75. This is the gradient. Since we are linearly interpolating the data, 24 minus 3 into 22.4 minus 3. Okay, so if you calculate, then you can easily get the effective depth corresponding to a hydrometer reading of 22.4. 20 minus 20.7 minus 75, 24 minus 3 into 22.4 minus 3, 8.45 centimeter. Okay, 8.45 centimeter. So this value would become 8.45. So in this way you can calculate the effective depth for other readings as well. Okay, so please calculate at your home. So 11.07, then 14.05, then 16.25, then 17.08, then 18.69, and finally 20.18. Now we know the effective depth. Now once we know the effective depth, we can use this equation. Suppose this is equation 1 and this is equation 2. Now by using these two equations, we can get the d centimeter and the d in centimeter, that is the particle size in centimeter, and the corresponding percentage final. Okay, now this eta value, this is given to this problem as 8.9 into 10 to the power minus 7 kilonewton second per meter square. Now please keep in mind, when you will be substituting this eta value, it should be in gram second per centimeter square, okay, in the CGS system. So that's why earlier I have mentioned that you please be very careful about the unit system which is basically involved in this type of equation. Again, for gamma is gamma W, you should use the correct unit. For HE, you should use in HE in centimeter and T in minutes. Now, after substituting all these values, because now we are having all these values, so we can easily calculate the D value for a specific time instant. Okay, so I am writing the values there. So please calculate at your home and let me know if you face any difficulty. So 0.052, then 0.030, 0.015, 0.009, 0.005, 0.002, 0.001. Now once this is done, then we'll calculate the percentage final. Now for percentage final, you need to know GS, that is 2.67 for this problem, then RC, that is the corresponding corrected hydrometer reading 22.4, 18, 13 and so on, and the W. What is W? W, this is the weight of solids per ml solution. Please keep in mind, for this problem we have basically mixed 40 gram of sample in 1000 ml water. So for per ml or unit ml solution, it will be 40 by 1000. Okay, so W value would be, here I am writing 40 by 1000. Now if you substitute the corresponding values, you can again get the percentage final, that is N 89.53, 71.95, 51.96, then 37.17, 31.58, 20.78, 10.79. Okay, now you may have a question that this table can be ended here. Why there is an additional column that is called percentage final on total? Why? Is there any logic that I have kept an additional column like percentage final on total? Do you think that there is a necessity for this additional column? Yes, there is a necessity, because most of the people do the mistake here. So this percentage final, whatever we have got, this is for the soil sample corresponding to retained on pan. Okay. However, when we will be drawing the grain size distribution curve, we have to draw the grain size distribution curve on the total basis. That means out of 500 gram. So here we have performed the experiment only on the basis of soil sample which is retained on the pan. Now in pan. Now how we can implement the correction factor for this kind of situation? So we have to basically multiply the corresponding percentage final with the percentage final which we have just now got. Okay, so this 21.96, this is the percentage final corresponding to 0.075. So this percentage basically retained on pan. This 21.96% of the out of 500 gram is basically retained in the pan, and from this pan we have taken only 40 gram of representative sample for the hydrometer test. Are you getting my point? So out of 500 gram, 21.96% is basically retained in the pan, and out of this 21.96 means how much? 78.04 how much it is? 21.96 into 500 divided by 100. So that means 9.8. So that is basically retained in the pan, and out of this 9.8 gram, 40 gram we have taken for the hydrometer test. Okay, so that means you have to multiply this N with the 21.96 to get the percentage final on the total basis. Okay, so this is for the this is with respect to the pan. Okay, percentage final corresponding to 0.075 mm. So if you don't apply this correction, then you will be doing a mistake. So this will be 89.53 multiplied by 21.96 divided by 100. Okay, so 89.53 divided by 21.96. So that means 19.66. Similarly, you will be having 15.80, then 11.41, then 8.16, then 6.93, then 4.56, then 2.37. Okay, so again I am repeating that I may be wrong in the calculation part, so please cross check all these values at your own. Okay. Okay, now this will complete the entire distribution. So here I have written, or here I have put as a whole. So up to this 0.075, you have got it from hydrometer. Sorry, sieve. Okay, so this is the sieve part, sieve analysis part, and this is the hydrometer part. Sorry. Okay, so it is nothing but a consolidated summary of the sieve analysis and hydrometer analysis. So 4.75, 98.88, then 0.075, 21.96. Okay, so 4.75, 98.88, 0.075, 21.96. And for the hydrometer, you have to bother about only this column and this column. So 0.05 to 19.66. So 0.05 to 19.66, then at the end 0.001, 2.37. So as you can see from the hydrometer reading data, it's quite obvious that the coarser particle will settle faster as compared to the finer particle. So 0.052, it's basically relatively or comparatively coarser than 0.001. So this will complete the entire grain size distribution data, means particle size versus percentage final. Now you have to plot this data in a semi-logarithmic plot as shown in this slide. So in the y-axis you will be having percentage final, in the x-axis you will be having diameter of particle, that is particle size, and in the y-axis corresponding percentage final. And y-axis it will be in the arithmetic scale, and x-axis it will be in the logarithmic scale. That's why it's called a semi-logarithmic plot. Okay, and the curve which you will be getting, that is called grain size distribution curve. So I didn't join the data points here. So after plotting this data, you have to basically join all this data by a smooth curve. sorry. Okay, so this is the GST curve. Now this is for today's session. So by using this plot, in the next week we will basically answer these two questions which we have framed for this specific problem, that is what type of soil is it and what is the gradation, means according to the coefficient of curvature and coefficient of uniformity, what is the soil classification, well graded, uniformly graded, gap graded. Okay, uh, I don't know whether you are familiar with these terms. So you must be accustomed with this type of terminologies by the end of this week. Okay, so please go through all the lecture videos. It's a sincere request from my side. So then it will be very effective. Okay, this session will be very effective. So so this is for today's session. Now it's your turn. So if you have any doubts or you need any further clarifications, you can ask. Okay, so this is one problem which is incomplete. We'll solve in the next or upcoming session. And there was one more homework problem. So this was a homework problem, and it is related to the previous problem only. Okay, so problem 5. So in addition to the grain size distribution curve, the this experiment related to this Atterberg limit test were also given in this problem, that is number of loss versus water content. And from that it was asked that if the oven dried remolded soil of 250 cc volume kept for 24 hours in oven weighs 595 gram, what is the shrinkage limit of the given soil? Okay, so it is an interlinked problem with the previous problem. So we'll again solve this problem in the next session. So with this uh, we have come to the end of this session. So these are the reference books which you can follow for this course. And this is taken from the screenshot of this lecture video. Okay, so Geology and Soil Mechanics. And okay, one more important information for all of you, that apart from this session which I will be taking, so there will be one more problem solving session, and which will be handled by one of my friends, Mr. Ashish Choudhury. So as you know that this session is scheduled on each Sunday from 5 p.m. to 7 p.m. So but that session is basically scheduled on each Friday. Okay, so from 6 p.m. to 8 p.m. And hope you have received a mail from the NPTEL office containing all this information. Okay, what is the meeting link and what is the time, duration and schedule. So any questions?